Hello, and thank you very much for the invitation to this wonderful conference. I'm sorry I can't be there with you in Egypt as my schedule didn't allow me, but I hope you're having a wonderful conference and greetings from London. I'm Manish Chan, Professor of Surgery at University College London, and I've been asked to give a short talk about artificial intelligence in endoscopy and surgery and some of the research work that we have been doing. Interestingly, if you look at this graph, you will see many familiar applications, items of software, technological advances that you use in your everyday life. But these things weren't around even 25, 30 years ago. And it's hard to think of a world without YouTube, without an iPad, without an iPhone, without Google, without Gmail, without Amazon. But these things have permeated every aspect of our daily lives. Unfortunately, we haven't seen such progress in healthcare and in particular in surgery. And the reason is this technology adoption curve takes a long time to get through. It takes many years of going through research and development until we enter a new phase of working. The new phase for us in 2022 is that of digital surgery. And there are many different definitions of what digital surgery is. But in effect, it is making data important and using data to inform our decisions. And that data comes in the form of digital data. So for me, and in my mind, the four pillars of digital surgery are image resolution, the use of extended spectral imaging, commonly known as fluorescence, the use of navigation and augmented reality, and then analysis of data under artificial intelligence algorithms so that we're able to support our decision making in a meaningful way using algorithms and using AI. AI is really an umbrella term. It's almost a colloquial kind of slang term that encompasses all kinds of different aspects of data and data inputs. We specifically in surgery and endoscopy are interested in computer vision, and computer vision and machine learning involve extracting data from the pictures that we see and the video footage that we see and building algorithms that allow the machine to learn aspects of the scene and what is to be predicted and what is to come. And then there are different types of methodology within that: supervised, unsupervised, and reinforcement learning. And I'll try and demonstrate some of that as we go along. AI in medicine is nothing new. We in surgery, as usual, are running behind our medical colleagues. Here are some of the examples in the literature across radiology, pathology, dermatology, ophthalmology, and other aspects of medicine. But in effect, what we're using is complex statistics and data analysis to allow predictions of what may or may not happen in the future. So this is what we've done before with predictive statistics, and we've used normograms, for example, within this context. But where artificial intelligence comes of its own, it learns iteratively from the responses that it makes. So as you program the algorithm, it will give you a predicted value, but it will use those values to better inform the algorithm so it's more accurate next time. It's like a chess computer learning as it goes and getting better and better and better. So why do we do it now? What's so special about AI in healthcare now? Well, these concepts are really around since the 1960s. But the reason why it's become easier to do now is because we have cheaper ways of storing data, so we don't have to use big factories housing reams and reams of data. And also, we're able to use far faster processing power. So if you think about the technology that took the first rocket to the moon, we can put that technology on a grain of sand now. Interestingly, you get these kind of headlines. Artificial intelligence can diagnose pneumonia better than your doctor. But what is that really saying? This is a paper from the Stanford group who built an algorithm that was able to identify patterns of pneumonia faster and more efficiently than a human physician. And that's not surprising when you think what it's doing. It is simply identifying a pattern on the radiograph. Where it begins to falter is if there's more than one diagnosis, for example. So we're not eliminating the need of a radiologist to check, but perhaps it is a way for computers to identify patterns faster and more efficiently, allowing the radiologist to be better deployed from a resource point of view, and then simply double check the results. So computer vision and machine learning, that's what we're interested in surgery. So we take the image or the video and we extract information that it's presenting to us. There is a wealth of information in that video data, from kinematics, the way that things move, to what is in the scene, how much is in the scene. For example, how much red is there? That means is there a lot of blood in the scene? What instruments, what phases we're in? And by using that data, we're able to make meaningful predictions. It's the same way that a self-driving car would work. Now, many cars at the moment, even ones that we currently own, have the ability to identify that there's traffic coming up, that there's a car too close to us, or that we may be swerving or changing lanes. And then they are able to auto-correct. And the reason that it's able to do that is because it is looking at data in real time using the algorithms that have been already put into the car and then giving you decision support. So it's a system which involves data input, data processing and analysis, and then an output. So here you can see, this is the dashboard, and this is essentially what the car would see. It sees objects on a road. The road is bounded by the two green lines, and it has to differentiate what those data inputs are. So there's a pedestrian, there are some cars there, there is a 60 mile an hour sign there, and it uses that data in the algorithms that have already been taught to it to understand how it needs to respond. And here you can see another example in real time, all the different inputs that are there. The distance between the car in front and the car that you're driving in, all of the different characters in the scene, what is going on in the scene, and therefore how to respond. And this is the kind of technology that we need to think about in surgery. So let's start with endoscopy and colonoscopy. What is the problem at the moment? Well, the problem are that we have, firstly, polyps that are often missed, so our adenoma detection rate may be low, and therefore cancers may be missed. And if we then look at the second problem, if we have polyps that are missed, are those polyps that we're seeing cancerous polyps, or are they hyperplastic polyps that can be ignored? So this is where we start from. How we use artificial intelligence in colonoscopy is to think about where the blind spots are, perhaps. So what is being missed? And those lesions that are in the visual field as well, but are not being detected. So we need better visualization of the mucosa in the first instance, and then when we are visualizing the mucosa, better scrutiny of that mucosa so that we don't miss things. We call this computer-aided diagnosis, and either we're interested in detection, so that is the identification of polyps, or characterization, what type of polyp are we looking at? So we've used optical diagnosis for many, many years. We look at what we see in front of us, and then we decide to do a polypectomy or to do a biopsy. And in this case, this study here that we see from the ASG Technology Committee looked at whether you can leave these polyps in or whether you can resect and discard them. And this is where we need to think about, are all the polyps that we are looking at, do they all need to be resected? Do they all need to be biopsied? Because ultimately, why are we resecting and biopsying polyps? It's because we're concerned that they may turn into cancer. And here's another example of a study where you can see that in the DISCARD-2 study, which was a multi-center study comparing surveillance intervals determined by optical diagnosis, so narrowband imaging, And you're looking at these surveillance sensitivity of 73%. So we want to augment and build on this kind of practice. This is what the algorithm would see. The algorithm sees a scene in front of it. It tries to understand what that scene is. So there are different folds, different layers, and then it looks for abnormality. So on the far right, you can see that there appears to be some sort of abnormality in that mucosa in the rectum. It is not telling you at this stage what it is. It is simply telling you that there is an abnormality there for you to consider. Early work involving AI and endoscopy simply looked at patterns and shapes and signals, and this was relatively basic. But these are important because we know that shapes and patterns and signals do tend to allow us to understand whether there is a polyp there, and if there is a polyp there, what type of polyp it may be. But going back to my earlier slides where I said, okay, we're taking this image, so we've got an input. We are then looking at various layers within that image, various data points within it, and how these deep neural networks work is that they look at layer upon layer upon layer, picking out important information that we can't see as a human being, and then they recreate an output. So eventually you can make sense of that wealthy data that you get from the video or photograph. We've seen this development being worked in early papers, and we've seen a lot of the work coming out of Japan and China with this. And you can see that we've got sensitivities of 90, 100% in some papers, but we're looking at good early data for us to build on. In this particular study by Wang et al., they looked at the increase of when you're finding polyps, the adenoma detection rate. And this is what's important because this is a surrogate marker of quality in colonoscopy. And we're looking at seeing whether by using computer-aided diagnosis, are we able to pick up more adenomas? And are we able to therefore see a statistical benefit in our study and then a clinical benefit to our patients? And here you can see the ADR rate is statistically significant. The mean number of polyps detected, statistically significant. And again, the mean number of adenomas detected, statistically significant. So this is essentially allowing us to use a tool that is improving on our abilities as an endoscopist. And we can use some of the commercially available tools, so GI Genius is one of them, and you can see that the adenoma detection rate increases. Here is an example of what it looks like in real time. So as you withdraw the scope and you're looking at the mucosa carefully, you'll see a blue box that goes round that area of mucosa. And it says, look, this is something which you need to look at and consider whether you need to biopsy it, whether you need to polypectomy it. And this is the type of work that we're beginning to see from our group. Again, this is one of our in-house systems. We're currently running the Caddy Trial. So you can see the colonoscopy configuration on the bottom left, and then you can see how in real time we're getting input of the mucosa, data processing against the algorithm, and then it moves on to a more augmented decision-making tool as an output shown in a green box. The next stage, characterization. When we get a polyp, we need to understand, is this an adenoma or is it hyperplastic? And again, we've always used pit patterns and various classifications to give us an understanding, but wouldn't it be great if we knew more definitively whether or not we needed to resect polyps because they were potentially precancerous? I think the translational challenges here are described in our paper here in the Lancet Gastrohepatology, is that you need to have collaboration here with industry partners because this type of research is expensive, requires important hardware and software, and it's important that we have open, transparent relationships with industry so that we're able to develop these tools in a much shorter time frame than we saw in the earlier sides of that technology adoption curve. So this is just an example of polyp characterization. Again, you're using the narrowband imaging. It's looking at patterns. It says that, look, this is something that you need to be worried about. And at the top, you can see it says adenoma. Here again, it's found another polyp. It will look at it in real time. And again, it suggests it's an adenoma. So it's using the various data inputs that are trained into the algorithm to tell us whether this is an adenoma or whether this, in this case, is a non-adenoma. So where are we in 2020s? Well, in the 2020s, there are commercially available devices such as GI Genius. What we need to understand, though, is what difference does it make if we improve our adenoma detection rates ultimately in reducing missed cancers or improving on cancer outcomes in the future? And that's what we'll be looking at over the coming years. This is our trial, the Caddy Trial, which is currently a randomized controlled trial in the UK, and we hope to be publishing on the interim results at some point in 2023. So this is just slides of the design phase, but I think we can skip those and move on to the surgery. So can we use the same sort of information and the same techniques in surgery? Well, of course we can, because we're getting video feed from the laparoscopic or the robotic endoscope, and it holds lots of data. Again, this is more of a technical slide, but this is essentially how the engineers and the computer scientists try and build out that data. And it's easier to see when we show you the kind of steps in surgical procedures. So this is a gallbladder operation, cholecystectomy being done. And in this particular screen on the left, we can see the phase of the operation that we're in. And on the right, it's telling us what tool has been detected. So this is called phase and tool segmentation. And it is important that the algorithm is able to detect which phase of the operation we're in. So we need to first divide the operation up into a series of steps, but also which instruments are being shown to us. Here's an example in real time of cataract work. Unfortunately, I've gone past that slide. So in effect, we can look at cataracts, or we can look at gallbladder operations, and in this case by our friends from Harvard, looking at laparoscopic sleeve gastrectomy. And the methodology here is quite straightforward for this type of research. You essentially have a set of data, and you divide that data up into training data to build the algorithm, and then to test it and validate it on. And this is a 70-30 split in this case. You segment the procedure, agree on what those segmentation steps are, and then you look at the assessments of those steps. And what we can see here is that the algorithm can detect the phase and the steps with great accuracy. So 80% in this kind of work is actually very good, and we're beginning to see algorithms now hitting up to the 90%. And this, again, we call this decision augmentation or clinical decision support. We can use it in other things. So here's an example of using it in Icg and fluorescence imaging. We know that if we use fluorescence imaging, we're able to decrease leaks, but we don't quite understand how, and we don't also understand some of the objectivity around when is Icg good enough to tell us that it is fine to create an anastomosis. But as I said before, a picture contains 1,000 words, which means we can extract lots of data of what we're being able to see. So in this slide, we can see on the top left of the colonic image, there is a perfused part of bowel shown with Icg, and what the algorithm needs to do is understand what is bowel, what is perfused bowel, what is ischemic bowel, and then also what is the background, what is the swabs. And once it can do that, it can allow us to build an algorithm to tell us where the optimal transection point is, based on the intensity of the pixels and also on the clinical outcome data that we've fed in. Because we need to know that we create an anastomosis which is distal enough to preserve colonic length, but also proximal enough to preserve perfusion. And here's an example of when we've used this to bring in experts to look at where is the optimal transection point. So here, most of us would choose E and B probably. And we use this as the ground truth. So when we build the algorithm knows that actually the transection point should be either E or B. So then it can build an AI platform around that. So in conclusion, computer-aided diagnosis in endoscopy and surgery, I think this is something that we're going to see a lot more of. It's all about data within the video footage, and taking that data, extracting that data, and using these computer vision and machine learning techniques to build accurate algorithms and ultimately improve our patient experience. Thank you very much, and I hope you enjoy the rest of the conference. I hope to join you for a Q&A session later.